Okay. So now on to our next amazing speaker, who is a John Koch Distinguished Professor, Department Chair of Electrical and Computer Engineering, and Professor of Computer Science at Duke University. He is a fellow of ACM IEEE AAAS and a Golden Core member of the IEEE Computer Society. Today, he will be talking about the journey of a researcher and dive into the digital microfluidics biochips. Please welcome Dr. Chakrabarty.
Okay, hello everybody. My name is Krish Chakrabarty. I hope you can see my screen. Thanks for the invitation. I will talk about computational intelligence or computational thinking as used to bridge engineering with microbiology and biochemistry. We have been working on this research for over 20 years, and we have gone through the process of coming up with new ideas, writing papers, patenting stuff, starting companies, and commercializing products. I want all of you to close your eyes and imagine the possibilities. We're looking at the future and we have to dream. Whenever you start working on a cool research problem, you have to imagine first. You can open your eyes at the end of the seminar. Okay, all right. It's fun, but it's also difficult because we do not know what lies ahead. So this is a quick outline. I will walk you through some motivation, give you some background on what is microfluidics, how does biochemistry and biology interact with engineering and computer science, and then get into the technology and talk about some commercialization success stories. I'll play some videos. I hope the videos will play well. And then talk about some of the algorithms, some of the techniques that we utilize to do optimization, because in the end, we need to ensure that our biochemistry runs quickly. We can get our outcomes of diagnostics fast, and also the chips that we build are small and cheap. And then I would end the presentation. So what is our goal? Our goal is to enable benchtop biomolecular assays, which are protocols that chemists or biologists run in a lab. We want to miniaturize all of that and make it run on a small chip, a microfluidic biochip or lab-on-chip. This chip is programmable, so we can write software that can be used to control the various operations that run on these chips. So essentially, you see this picture here where we have a lot of equipment in a lab, and we want to miniaturize everything and put that onto a chip. Of course, we cannot miniaturize the people. We can't shrink them and put them on the chip, but we want to capture their knowledge and enable the same intelligence that is available in the lab to be available on these chips. We want to keep these chips fairly simple because the users are not going to be computer scientists or engineers, but rather they will be doctors and nurses and technicians. But we want to enable realistic biochemistry, some real operations that can be run on these very simple chips. So we're seeing a paradigm shift in biochemistry. Basically, we used to have complex operations, microwell plates, a lot of test tubes, milliliter volumes of fluid, and we needed skilled technicians who had to be trained. They were prone to making errors, and bulky equipment that needed space and needed a lot of money to be acquired. Now we can do what is called lab on chip. So we can integrate a lot of components, reservoirs, wells, channels onto a small chip, the size of a PCB. This is called lab on chip. And why do we do this? Well, these are very small. So miniaturization helps in decreasing the amount of fluid volumes we need. And volumes are important because the smaller we can go, the faster we can run our chemistry. And the cost comes down if we can decrease the volume. Automation, less chance of errors. We can write software that can control these devices. And very high throughput, we can run lots of reactions in parallel. So very high throughput means that we can detect various conditions in a large number of people in a very short amount of time. So what is a biochip? I'm sure most of you haven't heard of this term before, so let me walk you through that. This is a miniature, so small, disposable. That is important. This is not meant to be used for a year or 2 years like your cell phone or your laptop. This is meant to be thrown away. So it has to be very cheap. And it does very high throughput sequencing or high throughput screening. So it's basically an instrument that does lots of things in parallel. What does it do? Well, all the chemistry that you are learning now in your classes in high school or in college when you will take chemistry, you would learn about dispensing, which is, you're going to be using micropipettes and your thumb will hurt because you'd be filling up test tubes with your micropipettes. Mixing, you would shake your test tubes to look at change in color. Does a gas come out? Is there a smell? Do you see some light? That is called detection. And then in the end, you throw away the content of the test tube safely. So we can do all these different things on a chip, but a lot cheaper and a lot faster. So this is the thing what a biochip basically does. So the main types of biochips, well, the first generation was passive. These were called microarrays. Essentially, you had a substrate of silicon or plastic or glass. And on the substrate, you would attach what is called a probe. And a probe used to be basically some DNA or protein. And then you would have to do a lot of the sample preparation and all the steps necessary in advance manually on a benchtop. And you would then introduce a prepared sample onto the substrate, the microarray, for the final step of binding. So there was something called hybridization. You would have binding between complementary base pairs on the probes. And based on that information, which you could extract by shining light onto the substrate and doing some signal processing, you would know what was in your sample. Now, what we are looking at is lab on chip or active systems, micro total analysis systems or micro tasks, where a lot of these functions are done on the chip itself. We do not need as much human in the loop. We can control the liquid flow. We can provide mechanisms for inputting samples and reagents. We can do pumping. We can do separations, even sensing. We could integrate all kinds of sensors to detect the endpoint of the reaction. Now, I mentioned cost, and this is a very important question because when you are running these reactions, you may not think about it too much, but cost matters. And you can see right now with the COVID pandemic, there's a lot of talk about can we run so many tests for so many different people because cost is a problem. This is a chart from EPFL. This is a Swiss university. And in the x-axis, we're looking at the cost in Swiss francs per unit weight, per gram. And you're looking at different materials. So copper, which is our interconnect in most of our integrated circuits today, in chips that we have, your Intel chips, for example, use copper interconnects. Copper is very cheap. So it's on the bottom left corner of the screen. And then you have silver, a little more expensive. Gold is more expensive. You make jewelry out of gold, and platinum, more expensive. Sapphire, diamond are even more expensive, right? But if you think about the antibodies that we utilize for doing all kinds of reactions, they are way up there. So they are more expensive per gram than even diamond. Okay, that is why we need to find techniques so we can reduce the amount of volume that we need. So when you're thinking about getting engaged and you want to buy a diamond ring for your fiance, tell your fiance that why diamond? Take antibodies. They're more expensive than diamond, right? Okay. So anyway, I wanted to make the point that volume does matter. We want to therefore run reactions not with milliliters, but with microliters and nanoliters of volume of fluids. So let's now look at microfluidics. This is a bridge. This is the technology that enables us to miniaturize and run reactions on a chip. So in the test tube world, the old days, everything was large. We had milliliter volumes. There was no automation, no integration, and no miniaturization. You can use robots. There are methods based on robotics where you can program a robot to basically pick up samples and reagents and place them elsewhere. So this gives you automation. It's overall integrated system, but it's very bulky, very big. So you can't really make it portable. You can run these tests in the field. With microfluidics, you get all the benefits. You get automation. You can run software to run these devices. It's all integrated. Everything is in a very small package, and things are small. So let's quickly look at the different technologies of microfluidics out there. So the older technology is based on continuous flow, where we basically have a substrate on which we can etch microchannels. So here you see the serpentine channels. You can have sensing as well. You can have all kinds of different shapes of the channels. The problem with this platform is that you cannot make these things very small. So if you make these things very small, the pumps or the electroosmotic fluid mechanisms, flow mechanisms, they tend to have reliability problems. And also the fluid flow can only be along these channels. So it's not reconfigurable. Instead, we have been looking at a platform where we used a patterned array of electrodes. So think about it as a XY coordinate system, and you have these electrodes arranged in an XY fashion. Each one can be accessed from an input pin. You can assign to it a voltage level, a high or a low voltage level. So that allows you to turn it on or turn it off. And the liquid is now transported in terms of droplets. Think of that as a packet. So this is the packetization concept. We're going from an analog world where we had continuous flow and analog signal to having individual bits. Think of a droplet as a bit of information. And this droplet can contain DNA and protein, can contain reagents, can contain samples. So this is my payload. And by turning on and off these electrodes, I can either hold a droplet at a specific location, or I can make it move. I can do all kinds of interesting things. So this is called digital microfluidics. And the rest of the talk, I will be focused on this platform. So let's look at the science behind microfluidics or droplet-based microfluidics. The basic physics is called electrowetting. The concept goes back to the 19th century, not a new concept. And the idea is that when you have a droplet that is very tiny in volume, you go down to the nanoliter or even smaller picoliter volumes, the bulk forces are weaker than the surface forces. The surface forces start to dominate. And now if you have an electrode, and on that you have a thin insulator, and on the top, I have not shown in this picture, there is a very thin hydrophobic layer. So you coat it on top of the insulator. Now, if you bring a droplet of liquid, which is very small in volume, because of the surface forces being dominant, the droplet makes a nice spherical shape with a large contact angle. If I now apply an electric field between the electrode and the droplet, it basically changes the surface from being hydrophobic to hydrophilic, and the droplet now wets the surface. Okay, so essentially there is some energy being introduced into the system, and the energy would be modulating the surface tension, the surface forces, and the droplet would wet the surface like this. If I now take the electric field away, the droplet would bounce back to the original position. So this is the nice thing about the system. So you can think about the voltage as a high or a low voltage, a 1 or a 0, and that can be used to change the state of the system. So I'll show you here a video of a droplet on a surface. When I start the video, you will see that there is no electric field. The droplet stays there. Then after a while, you will see one oscillation. And then if I increase the frequency of actuation, the droplet would move faster. So let us see how this movie looks. So this is the first time, and now I'm doing it with much higher frequency, and you can see the droplet going up and down. I can now go from having a droplet which is going up and down to making it move in a lateral fashion. So from this picture here, continuous electrode with a droplet on the top, I can have now multiple electrodes with gaps in between, and a top plate, which is permanently kept at voltage level 0. Now, if I want to hold a droplet at this location, I would apply a high voltage in the middle, and I would apply low voltages on the two ends. So think of this as a 0, 1, 0. There's no net force on the droplet. It will stay there. If I want to make it move to the right, I would apply a high voltage on this electrode here on the right, and a low voltage on the two other electrodes. So that means I have a 0, 0, 1, and that exerts a net force to the right, and the droplet will move. And the same way I can make it move to the left. So this is a video of looking at it from the side, and you will see a droplet marching left and right. There you go. So we're just adjusting the voltages on the electrodes. We don't need any pumps. It's all electrical. Just control the voltage levels, and you can make the droplet do all these things. Now, there is one interesting caveat here. Because the volume is so small, there could be evaporation. So we have seen experiments where after a few minutes, the droplet just disappeared. Poof, where did it go? Well, it evaporated because it is nanoliter, picoliter volume. So we have to use a film of oil. It's an inert silicone oil that prevents evaporation. And also it prevents cross-contamination, because if you're transporting large molecules, DNA, protein molecules, they may stick to the surface and cause contamination. So when you use oil, you eliminate the chances of contamination. You can now think about this from a computer science perspective as a finite state machine. So the system has a state, which is basically an n-bit vector. N is the number of electrodes, and each vector is 1 or 0, whether the electrode is turned on or turned off. And anytime you make a droplet move, you are doing a state transition. The system moves from one state to some other state. Okay? And you can move multiple droplets at the same time. Each droplet consumes only 1 microwatt of power. So we can have 1,000,000 droplets being simultaneously actuated, and the power consumption on this chip would be just 1 watt. Okay, so next I will show you a view from the top. Looking down on this array, a droplet is going to be routed to the east, north, west, and south, and very quickly. This is actual speed. This is not simulation. I have not done any adjustments. This is the real speed at which I can move a droplet. You can see that the transportation is very rapid. Then I will show you 2 other videos. The first one is actually inputting a droplet into the system. So this you can think about as the interface to the outside world. The outside world is not droplet. The outside world is bulk liquid. You have large volumes. So you can have a reservoir which can be filled with liquid. And then what you can do is you can inject a droplet into the system by controlling the voltages on the line of electrodes here. I can control the voltages here. So I can start with a 1 here and a 0 there. Then I make this 0 and make this 1. And as I do that, I would create a neck, and I can break the neck. And the droplet would enter the system. So this is my basic input operation. Think about this as an A to D converter, analog to digital converter. So you can see that I can with very high accuracy, I can inject these droplets. And we have done this billions of times, and we are seeing less than 0.1% volume variation. The next video is a dance. Basically, there are now multiple droplets. Each one is being controlled very precisely by software so that they can move around simultaneously and they don't have any accidents. They don't collide. We can track them very precisely. So there you go. This is a choreographed dance of droplets. Okay. Now what this tells us is that I can run multiple reactions on the chip at the same time. I can do multitasking. I can do parallel processing. This is like pipelining. We can run different threads of control on this chip at the same time. So of course, this was very attractive. We got a lot of interest from companies, and we basically started our own company from Duke. It was called Advanced Liquid Logic. And around 2011, this was one of the early products. So this was the PCB platform we had fabricated. So the reservoirs are on the edges. These are for the various samples and reagents. And then we had electrodes in the middle for transporting the droplets and doing incubation mixing. And then there was a sensing area. And then the package would be placed here. This was the instrument. And the instrument had power supplies, control software, memory, all built in. And the user would see things on the screen. So this was not a very small chip because it was a PCB device. But it was actually of great interest to 2 counties in Illinois. There were 2 counties that mandated that every newborn in their hospitals was going to be tested with these chips. So during that period, the company was selling 5,000 of these chips a day. Now you may think it's a very large number, but these are very cheap chips, right? You throw away, so there's not much of a margin. But still, it was great to see so much interest in these chips. And then there was an acquisition in 2013. Illumina, which is the world's largest DNA sequencing company out of San Diego, they bought ALL. And at that time, their senior VP said that they were going to be using this technology for the next generation sequencing workflow, which means they will use it for sample preparation. So for sequencing application, you have to prepare your samples in a whole range of concentrations, even the reagents. So 1 molar, 0.5 molar, 2 molar, and then you need to have the library created so that you can use it during the sequencing. And this is a very tedious process. So if they could automate that using our chips, that would be great. Now, very quickly, within a year, they transitioned this to a product, and there was an announcement in 2015. Illumina announced the NeoPrep library system that essentially uses these chips. And I'm going to show you a video from Illumina. I hope the sound would work out okay. Let me maximize the sound here. And let's hope this plays well. So you're seeing here a scientist, and she's very tired from working very hard on all these things, and she's going to wipe her brow, and then she'll look up and see light, and then you'll see that the Lululemon chip come into play. She's tired, exhausted. So you can see that we went from research to commercialization, and there was a product in about 2 years. And then there is a company called Genmark that has also licensed this invention, and they are using this for nucleic acid extraction, amplification, and detection, all done in 2 minutes of time. They have a platform called ePlex, and I will play a video from them.
Genmark is pleased to present the future of molecular diagnostics. ePlex, a sample-to-answer multiplex molecular diagnostic system, delivers laboratory efficiency and rapid comprehensive clinical results for clinicians and patients. ePlex features enhanced workflow, enabling optimal use of staff time. Simply load the patient's sample into the cartridge, scan the cartridge barcodes for positive sample identification, and load the cartridge into any bay. The visually appealing user interface is intuitively designed to meet the unique needs of laboratory professionals. The fully integrated cartridge contains all required reagents, simplifying sample preparation. ePlex fully automates molecular testing, including sample preparation, extraction, amplification, and detection to deliver rapid sample-to-answer results.
So as you saw in that movie, they are able to move these droplets really fast, much faster than you can do at the university. And this is pretty common because once you commercialize, you have to make a product, and a product is of course a lot more effective than the university prototype. Okay, so with that, let me move to the next part of the presentation, which is about how do I optimize these systems? Because in the end, my goal is to complete my reactions in the shortest possible time using the minimum possible volume of reagents and sample and ensure very high reliability. So you can think about this now in terms of algorithms. So we are talking about a specification of the biomedical assay. What do I want to do on these chips? So I take some samples and from a patient like plasma, urine, saliva, and then I would do all kinds of assays or tests on those samples. I could do them one by one, but that is very slow. Instead, can I do them in parallel? So I can think about doing an architecture level synthesis where I find out more or less the top level chip plan, and then look at the macroscopic structure, look at the scheduling problem, in what order I run the different fluidic operations, the binding problem, which basically says to what unit on the chip do I map each operation. And then I look at the microscopic structure, the actual layout. Where do I place the different modules, what kind of routing I do, and I get the full layout of the chip. Okay. So essentially, I'm talking about two kind of engineering problems. One is called fluidic-level synthesis, and the other is doing the actual chip design. So I'm talking about the sequencing graph model. I have to formulate the problem in terms of some mathematical construct. And the construct we're using here is actually a graph model. Every node is an operation, and the edges indicate that they should be done first. So which one gets done first? And then I'm talking about scheduling. So this basically tells me in what point in time different operations get scheduled or run, time assignment. And then I look at the placement. Where do I put the different modules on the chip? What kind of transportation pathways do I use to transport the droplets? And then the chip level design, basically what I have is I have the electronics going underneath the microfluidic layer. I have the fluidics on the top, and below that I have the wiring that is used to control the electrodes. So I need to know which electrodes get utilized at which point in time. And then I have to think about my control pins. I have to now add IO pins to the chip so that I can use these IO pins to provide the voltages to turn the electrodes on. And then I have to do the actual wiring, connect the IO pins to the various electrodes on my device. Okay, these are all very interesting problems in engineering. There are algorithms we can come up with to do optimization. A problem that I want to showcase here is about droplet routing. So routing is the problem of transporting droplets from point A to point B in the shortest possible time. Now, if you think about VLSI or very large scale integration or in ICs and chip design, we also do a lot of routing. We have wires. We lay out wires that can connect point A to point B on the chip. So in that sense, the problem is similar to interconnect routing in complex chips, but it's not the same problem, because if you look at a VLSI chip, you have an actual wire. But when you look at microfluidics, it's a virtual pathway because there's really no wire. I can program the electrodes to act as a transportation medium. Once the droplet is transported, I can reuse these electrodes for doing other things. So we think of this as the problem of routing of trains. When you have a train being routed, the tracks can cross each other. That's fine. That's not a problem. But the trains must not come at the same time at the intersection. So we must have control mechanisms to guarantee that no two trains would collide at this intersection. So we do the same thing here in droplet routing. A second problem is about pin constrained optimization. So I may have 10,000 electrodes or even more on a chip. And ideally, I would like to control every electrode by an independent pin. But that is impossible because the IO pad frames are much larger than the electrodes. I really cannot have 10,000 pins on the chip. So I can probably do only about 1,000 pins or 500 pins on the chip, but I should be able to use them to control all the electrodes with no impact on throughput. Okay, now one option is I can move one droplet at a time, and then I can have a small number of pins, but that is too slow. So I would like to therefore have very high throughput and find a way to do parallelism. So one way is to use what is called cross-referencing. I basically use X and Y coordinates to control every electrode. So instead of having an n by m, I have n plus m, n rows and m columns. Okay, so use row and column addresses for every electrode. So think about this as an array. I have 10 rows and 10 columns. I have 3 droplets on the array, and I want to move 1 and 2 as shown. So to do that, I have to turn on the columns and the rows. The destination rows and columns get turned on, and that would allow the droplets to be moved. But I have destination cells. I have unintentional destination cells. When I move 1 and 2, I also move 3. This is a problem. So the question is, if I have many droplets like this on the array, 9 droplets, do I need 9 steps to move them one by one? That is very slow. Or can I move them in parallel? Can I find a way to move as many of them at the same time as possible? Now, this problem can be modeled in terms of some mathematical framework. The question is to find an optimal grouping plan. So put these 9 droplets in groups so that all the droplets in the same group can be moved at once. And the number of steps you need is equal to how many groups you have formed. So the insight we can draw here is that we look at the destinations. If 2 droplets have a common destination row or column, then we can move them at the same time. Okay, this is the insight we get. Once we get that insight, now we can go from biology and chemistry to computer science and mathematics. We can draw a model. This is a model of the array, and the model has nodes and edges and a graph. Every node corresponds to a droplet, and 2 nodes are connected by an edge, if they have a common destination row or column. Okay, so for example, if you look at this graph here, 1 and 2 have a common destination column. Therefore, you have an edge between 1 and 2. But there is no edge between 1 and 5 because they don't have a common destination row or column. So I first draw this graph, and then I do a clique partitioning on the graph. A clique is a maximum subgraph, basically a graph where every node is connected to every other node. And this is a very well-known problem in graph theory. So I would do a clique partitioning. The number of cliques I have in the graph tells me how many steps I need to move the droplets. And all the droplets in the same clique can be moved at the same time. So in this particular case, we need 3 steps, and not 1, not 9, but we need 3 steps to move the droplets. You can also think of this problem in terms of what the voltages you need for the electrodes. So we have talked about 1 and 0. There's also a third level, which is called an X. I don't care. For example, if I have a droplet which is to be kept here, I need to make sure that this is 1. The neighboring electrodes must be 0. But the one here, I don't really care. Can be 1, can be 0. So it's an X. So now if you think about the actuation sequence over time, essentially you have these 9 electrodes as shown here. Sorry, there are 8. This one is not marked. You can think about this over time, a sequence of actuations, and each vector is consisting of 0, 1, and X. Now the question is, can I map the X's intelligently to 1s and 0s so that I have as many columns being identical as possible? If 2 columns become identical, then I can control those 2 electrodes with the same input pin. Okay, so I need to therefore find a way to map the X's such that the number of distinct columns is minimized. Okay, and this can also be mapped to a problem of clique partitioning, or in graph theory. Every electrode can be modeled as a node in a graph, and I have an edge between 2 nodes if the 2 nodes are compatible. And what that means is that in any time frame, in any row of this table, they don't have opposite specified values. So for example, here in the first cycle, this has to be 0, this has to be 1. So this is incompatible, and therefore I cannot have an edge between those 2 nodes in the graph. Okay. So I look at compatibility, I create the edges, and then I do a clique partitioning on the graph. The number of cliques in the graph tells me how many input pins I need, and all the nodes in the same clique can be controlled by the same pin. Okay. So you can use a very nice algorithmic method to do optimization on these chips. So with that, I come to the final few slides. So what I've given you is a flavor today. Digital Microfluidics offers a very attractive platform for doing lab on chip for clinical diagnostics and biomolecular recognition. We are using a lot of automation methods from computer science, from algorithms, so that we can control using software, the droplets, and doing the reconfiguration. I talked about some commercialization success stories. There are products now which are using these kind of chips. Some numbers in case you're interested. So we have been able to work with 11.4 volts to dispense droplets and 7.2 volts to transport them. These are the smallest voltages we have used. We are using different materials as our hydrophobic layer and insulator. The smallest chips, we can work with 12 picoliter droplets on 33 micron electrodes. And we've also done 5 picoliter droplets on 21 micron electrodes. So the final slide is, we now have a biochip ecosystem. So on one side, we have the folks who are building the chips, who are actually doing the chip fabrication. And then we have the users, the different medical diagnostic labs, nurses and doctors. And then we have software. So this is the bridge that is connecting these 2 entities and allowing us to make the best possible use of these chips. Okay, that's the end of my presentation. Thanks a lot. Let me see if you have any questions. Let me stop sharing and check in chat. I see one question in chat. Is that for me? No, that's not for me.
I have a question.
Yep, sure, go ahead.
Do they do any of this digital microfluidics research somewhere in the Bay Area or California?
Yes, so this is a research field which is fairly large now. So there is ongoing research at Stanford, at Berkeley, at UCSF, and there are companies as well, mostly spun out of university labs. which are looking at further commercialization. So yes, the answer is that these are not in large companies. You don't see this advertised in the front, but if you look inside their corporate labs, they have ongoing activity as well.
Okay, if that's all your questions, thank you so. Oh, there's another one. We are running a little bit low on time, and I know Dr. Chakrabarty, you also have another commitment.